I could tell you that light is made of photons. I could tell you that it behaves like a wave. I could tell you it travels at 186,000 miles per second. I could tell you about electromagnetic fields oscillating perpendicular to each other. I could fill this whole hour with formulas and equations and diagrams. But would you understand light? Would I understand light? Let me tell you something that might surprise you. I don't understand light. Not really, and neither does anybody else. Nobody understands light. We can describe it, we can predict what it will do with fantastic accuracy, but understand it, that's a different matter entirely. Now you might say, wait a minute, Feynman, you won the Nobel Prize for work on light and matter. You must understand it. But that's exactly the problem. What do we mean by understand? See, there's a difference between knowing the name of something and knowing something. There's a difference between being able to calculate what will happen and understanding why it happens. Let me give you an analogy. Imagine that the world is something like a great chess game being played by the gods, and we're observers of the game. We don't know what the rules are. All we can do is watch. If we watch long enough, we might catch on to a few rules. We might notice, for instance, that bishops always stay on the same color. Aha, we write that down. That's a law. Then later we figure out something deeper. Bishops move diagonally. That explains why they stay on the same color. We feel pretty good about ourselves. That's what we do with light. We watch what it does and we figure out the rules. The rules turn out to be quantum mechanics, and those rules let us predict what light will do in any situation we can think of with absolutely remarkable precision. But do we understand it? What do you mean by understand? Here's the thing about light that drove people crazy for centuries. Sometimes it behaves like a wave, and sometimes it behaves like a particle. Newton thought it was particles, little corpuscles flying through space. Then came people like Young and Fresnel, who showed that light makes interference patterns, like waves in water. They could make light interfere with itself. You shine light through two slits, and you get bright and dark bands on a screen. That's waves interfering, no question. So everybody said, aha, light is a wave. Case closed. Except then, in the early 1900s, people started doing experiments that showed light comes in lumps. Einstein explained the photoelectric effect by saying light comes in little packets of energy, photons. When light knocks electrons out of metal, it doesn't do it the way a wave would. It does it like particles hitting the electrons, one at a time. So which is it, particle or wave? And here's where we have to be very careful. The answer is, it's neither, or both, or something else entirely that we don't have words for because nothing in our everyday experience behaves this way. You see, light is light. It's quantum mechanical, and quantum mechanical things don't behave like anything you've ever seen in your ordinary life. Everything in your experience, everything you're familiar with, is made of big things. Baseballs, rocks, people, cars. And big things are made of atoms, but there are so many atoms involved that the quantum effects wash out. You never see a baseball behaving like a wave. But light is different. Photons are individual quantum objects, and they behave in this strange way that isn't like waves and isn't like particles. Let me tell you what happens when we try to understand this. Let's do an experiment. We set up a light source. We put a screen with two holes in it, and we put a detector on the other side. We shoot photons at the screen. Now, if you ask me, which hole does the photon go through? I have to tell you something peculiar. If you don't look, if you don't check which hole it goes through, you get an interference pattern, bright and dark bands, just like a wave going through both holes and interfering with itself. But wait, you say, that's nonsense. A photon is a particle, a single thing. It must go through one hole or the other. So you set up a detector to see which hole it goes through, and you can do this. You can detect which hole each photon passes through. But here's the kicker. When you do that, the interference pattern disappears. Now you get two bright patches, right where you'd expect if particles were going through two holes. What does this mean? When you don't look, the photon seems to go through both holes at once and interfere with itself. When you do look, it goes through one hole or the other. The photon seems to know whether you're watching. Now you might say, well, obviously when we detect which hole it goes through, we must be disturbing it somehow, and you're right. But here's the thing. It doesn't matter how gentle we make our measurement. Heisenberg showed us this. He proposed what's called the uncertainty principle. It says you cannot design an apparatus to determine which hole the photon goes through that won't disturb it enough to destroy the interference pattern. It's not a matter of our equipment being clumsy. It's nature itself that prevents us from knowing both things at once. This is not like anything in our normal experience. If I roll a ball down a bowling alley and it veers to the left, I can figure out why. Maybe there was a breeze, maybe the floor wasn't level, maybe I put spin on it, but with quantum mechanics, nature says we can only predict probabilities. We can't say exactly what will happen. We can say if we shoot a photon at a piece of glass, there's a 4% probability it will reflect and a 96% probability it will go through. But which one will this particular photon do? Nature doesn't tell us. It's not that we don't know. Nature itself doesn't determine it until it happens. This bothered Einstein terribly. He never liked quantum mechanics. He'd say, God doesn't play dice. He thought there must be some deeper theory, some hidden variables we're missing that would tell us exactly what will happen. But experiment after experiment has shown that he was wrong. Nature really is probabilistic at the quantum level. That's just how it is. Now, do I understand this? No. It's completely crazy from the point of view of everyday experience. But I can calculate what will happen. I can use the rules of quantum mechanics to predict the probability that a photon will reflect off a piece of glass, the probability it will be absorbed, the probability it will be emitted by an atom. And these predictions are accurate to 10 decimal places. They're the most accurate predictions in all of science. So what does it mean to understand light? Maybe understanding means being able to predict what it will do. By that standard, we understand light very well indeed. Or maybe understanding means having an intuitive feeling for why it behaves the way it does, being able to picture it in your mind. By that standard, nobody understands light. Nobody can really picture what's going on. Here's what I think. The problem is that we're trying to understand quantum mechanical behavior using concepts from everyday life. We use words like particle and wave because those are things we know. But light isn't a particle in the way a baseball is a particle. And it isn't a wave in the way water waves are waves. It's something else, something new. The mathematics describes it perfectly, but we don't have everyday analogies for it. Let me give you an example of how precise our understanding is, even if it seems crazy. When a photon can take multiple paths from point A to point B, we calculate an amplitude for each path. The amplitude is a complex number. It has a magnitude and a phase. We add up all these amplitudes for all the possible paths, and the square of that sum gives us the probability that the photon will arrive at point B. Now here's the beautiful part. Different paths contribute different phases. Paths that take the same time contribute phases that are in sync. Paths that take different times contribute phases that are out of sync. When you add them all up, usually they cancel out. Most paths contribute nothing. The only paths that matter are the ones near the classical path, where the time is at a minimum. That's why light seems to take the shortest path. It's not that it chooses that path. It's that when you add up the amplitudes for all paths, the ones far from the classical path cancel out. This method, by the way, is called the path integral approach, and it works for everything, not just light. You can use it to calculate what electrons do, what atoms do, everything, and it gives the right answer every time. But does this make sense? Can you picture a photon taking every possible path at once? I can't. And yet that's exactly what the mathematics says. And the mathematics is right. We've checked it billions of times. So when someone asks me what light is, I have to be honest. I can tell them how light behaves. I can show them the equations that predict what it will do. I can even give them a quantum mechanical description in terms of photons and quantum field theory. But if they ask me what it really is, what's actually going on, I have to say, I don't know. Nobody knows. And you know what? That's okay. That's part of what makes physics exciting. We don't understand everything. We probably never will. But we keep trying. We keep pushing. We figure out the rules of the game, even if we don't understand why the gods chose those rules. The wonderful thing about physics is that even though we don't understand why nature works the way it does, we can figure out how it works. And that's an incredible achievement. We can take something as fundamental and mysterious as light and reduce its behavior to mathematical rules that we can apply and predict with. Here's something else that's important. As we've learned more about light, things have actually gotten simpler in some ways. It used to be that we had this big mystery. How can light be both a particle and a wave? But once we accepted that quantum mechanics is just the way nature works, that mystery dissolved. It's not that light is sometimes a particle and sometimes a wave. It's that our old concepts of particle and wave don't apply. Light is a quantum mechanical object, and it obeys quantum mechanical rules, period. And those rules, by the way, are beautifully simple. There's just one rule, really. Calculate the amplitude for every possible way something can happen, add them up, and square the result to get the probability. That's it. That's all of quantum mechanics in one sentence. Everything else is just working out the details. The theory that describes light interacting with matter, quantum electrodynamics, or QED for short, is the most successful theory in all of physics. It can predict things like the magnetic moment of the electron to 11 decimal places. 11, that's like predicting the distance from Los Angeles to New York to within the width of a human hair. No other theory in science comes close to that kind of precision. And yet, even though we can calculate these things with such incredible accuracy, I still can't tell you what a photon really is. Is it a little ball? No. Is it a wave in some medium? No. Is it a disturbance in the electromagnetic field? That's closer. But the electromagnetic field itself is a quantum field, which means it's made of photons, so we're going in circles. The honest answer is that a photon is whatever it needs to be to obey the rules of quantum mechanics. It's a mathematical object that behaves according to certain equations. When we measure it one way, we see particle-like behavior. When we measure it another way, we see wave-like behavior. But it's not really either one. It's just a photon. Now, I know this is frustrating. You want me to tell you what light is. You want a picture you can hold in your mind. But I can't give you that, because light doesn't behave like anything in your experience. The best I can do is give you the mathematical rules and show you how to use them. But here's the thing. Once you accept this, once you stop trying to force quantum mechanics into classical concepts, it becomes much easier. You stop asking, but how can it be like that? And you start asking, what will happen if I do this? And that second question we can answer. So what does it mean to understand light? I think it means different things at different levels. At the deepest level, maybe nobody understands it. We don't know why nature chose quantum mechanics. We don't know why the rules are what they are. But at a practical level, we understand light very well. We can predict what it will do. We can use it to build lasers and fiber optics and solar cells. We can manipulate it, control it, measure it with incredible precision. And isn't that a kind of understanding? Maybe not the intuitive, gut-level understanding we have of things like baseballs and water waves, but it's a deep mathematical understanding that lets us see how light fits into the whole structure of physics. The most amazing thing about light, I think, is that it connects to everything else. Light is the carrier of the electromagnetic force. That means it's responsible for almost everything in our everyday experience. The fact that you can see, that's light. The fact that atoms hold together, that's the electromagnetic force carried by photons. Chemistry, biology, all of it depends on light and electromagnetism. When you understand light, you understand one of the four fundamental forces of nature. You understand how energy travels across the universe. You understand why things have color, why metals reflect, why glass is transparent. You understand a huge chunk of how the world works. So maybe that's what it means to understand light. Not to have some comfortable mental picture of what a photon is, but to see how it fits into the whole tapestry of nature. To see how the rules governing light connect to the rules governing everything else. To see the simplicity and beauty underlying all the complexity. And if you can do that, if you can see light not as a mysterious thing, but as a natural consequence of the laws of quantum mechanics and relativity, then you understand light about as well as anyone ever has. But remember, that understanding is based on mathematics, on equations, on rules we've discovered by watching nature play her chess game. It's not the same as everyday understanding, and it never will be, because light is fundamentally different from everyday objects. The key is not to be frustrated by this. Don't say, but I don't understand how a photon can be in two places at once, because you can't understand it that way. Nobody can. Instead, learn the rules. Learn how to calculate what will happen, and then marvel at how well those rules work, how accurately they predict what nature will do. That's what I do. I've spent my whole career working with quantum mechanics, and I still think it's bizarre, but I've learned to use it. I've learned to trust the mathematics even when my intuition rebels. And that, I think, is the best we can do. So what does it mean to understand light? It means accepting that light is quantum mechanical. It means learning the rules of quantum mechanics and how to apply them. It means being able to predict what light will do in any situation. It means seeing how light connects to the rest of physics. And it means being okay with the fact that you can't picture what's really going on in any classical sense. If you can do all that, then you understand light about as well as any human being can. And that's pretty good. Not perfect, not complete, but pretty damn good. And who knows, maybe someday someone will come up with a deeper theory that makes it all make sense. But until then, we have quantum mechanics, and it works beautifully. So don't be discouraged if light seems strange. It is strange. It's one of the strangest things in nature, but it's also one of the most fundamental. And understanding it, even in this imperfect way, is one of the great achievements of human thought. That's what it means to understand light.